Welcome to the hardware technology track. We're going to start with a talk on MicroTCA at ESS by Simone Farina. Simone is an electronics engineer working in the Integrated Control Systems group at ESS as an embedded systems engineer. His main focus is on the deployment of systems based on MicroTCA and on firmware development. And in the past, he worked as a hardware designer and firmware developer for cards embedding FPGAs, including MicroTCA AMC cards. Thank you.
Thank you for the introduction, and good morning, everyone. So I will be talking about the MicroTCA generic data acquisition system at ESS. And this talk will basically cover the following topics. I will first start by giving an overview of what MicroTCA is, for those of you that are not yet familiar with the standard. Then I will start talking about what are ESS requirements for the MicroTCA systems. This will also include discussion about what ESS wants to bring to the MicroTCA community by different contributions. Then I will move to the generic data acquisition system platforms that have been developed and are now in use at ESS. And I will conclude the talk showing about a few system showcases that use this hardware that has been developed. Yesterday, there was a talk about EtherCAT, and we already saw there that ESS wants to deploy a multi-layered systems where MicroTCA will actually be used for the most demanding applications. But why MicroTCA? MicroTCA is, first of all, a modular standard. This means that the constituent cards of the MicroTCA system, which are the AMCs, and we will see shortly what they are, allow, by installing more of this card inside the same crate, to achieve many different instruments and cover many different purposes. But there is also another more important aspect of MicroTCA, which is the manageability of the standard. And this provides as main features an high availability, manageability of the system, redundancy if it needs to be included, and of course, easy serviceability of the same system. This is what a complete MicroTCA system looks like. We have cooling units, the MicroTCA carrier hub, redundant power modules, and up to 12 AMC cards. This will be the card that actually make the work, for example, for the acquisition and computational of the different algorithms. What is important in this slide that I would like you to focus on are the orange parts of it. So the part that are responsible for the management of the systems. We have the MCMC, which is the MicroTCA Carrier Management Controller, which is basically responsible or collecting data from the management section of all the cards and reading if they are in full operational status. It also provides information about which communications are required by the different cards and allows you, the operator, to take action if something is going wrong with the system. For example, if a sensor reading temperature is going above threshold levels, you can take action on it, or you can also instruct the system to shut down the card if it's really needed. All this communication is done by use of EPMI packets on EPM bus lanes, which are E2C compatible lanes. This is what MicroTCA offers for an interconnection point of view, excluding the management part. As we can see, we have redundant gigabit Ethernet connection on port 0 and 1 for the different AMCs. We have board-to-board fast links on port 2 and 3. Then we have the most important interconnection media for the entire system, which is called the FAT pipe and extended FAT pipe, which for our application at ESS will be PCI Express, but could be, for example, 10 gigabit Ethernet or XIWAY. And then we have what the standard defines as extended option region, which are additional board-to-board communication. For what are our application, the most important will be port 17 to 20, which are dedicated, in this case, for multi-drop LVDS bus. Then, of course, we have different clock available for all the AMCs. And the last one, which is the factory clock, is the one that provides reference for the fat pipe. Going now to what are ESS requirements for the MicroTCA systems. We have to keep in mind that ESS plans now to start deploying around 500 MicroTCA systems in the facility. This will cover applications like the beam diagnostic, the RF systems, including the low-level RF, and the fast part of the RF local protection will be also implemented using MicroTCA. The fast beam interlock system for the machine protection, a part of it will also rely on MicroTCA equipment. And the timing system will be used in most of this to provide synchronization and trigger for the acquisition. What ESS wants to achieve is to have a system availability that will be greater than 95%. This is well matched by MicroTCA capabilities because the standard, when you're using all of the features for manageability and redundancy, guarantees an uptime and availability greater than 99.9%. This is what the standard aims because it's based on telecommunication and wants to retain the same stability and availability that's needed for those purposes. ESS wants to contribute to the MicroTCA community in different ways. First, we want to rely as much as possible to customer off-the-shelf infrastructure by buying infrastructure equipment. But there are a few cases where this was not possible, and I will cover it in the next few slides. But then what we will do is interact with the manufacturers in order to get new developments done so that new customer off-the-shelf equipment can be released. ESS is also highly driven by in-kind projects. And through the in-kind project, we will receive additional hardware, additional AMC cards. So the most important that will be also about a few of those I will talk later in this presentation are a new revision of the event receiver, the development of an FMC carrier, the development of digitizer cards, and also the development of RTMs that are connected directly to the AMC through the Zone 3 connector. I was saying in the previous slide that we interacted with the manufacturers to revision current products. This is an example. ESS wants to use front-rear cooling scheme, and it needed a small MicroTCA crate for those applications where the use of 9U crate was impractical because of size constraints. What was already available on the market was the backplane depicted here, but this was not fully suited for our application because the trigger lines were not spanning the whole backplane, so they were not available for all of the AMC cards. This, through interaction with the manufacturer, we were able to change, and actually a few months ago a new revision of this backplane was released. What we have now is that we sacrificed the throughput on a few interconnections on the fat pipe, so we switched from 16 lane PCI Express to 8 for all of the cards. But what we gain now is that we have bus and VDS lines that cover all of the cards and allow our timing system to provide triggers to all of the remaining cards in the system. Going to talk about the cards that have been developed as in-kind projects. The first one that I will talk about, and is the one that gives the title also of the talk, is a generic data acquisition platform, which is an FMC carrier card developed by the in-kind contributor from PSI and on their behalf by Yoxos Technologies. This card embeds a PowerPC CPU, a T2081 from NXP, and it embeds also the latest family of Xilinx FPGAs, a Kintex UltraScale. These cards provide a CPU section with dedicated 2 GB DDR3 memory, which also has a direct connection on the gigabit Ethernet on backplane. This CPU communicates with the FPGA on board through PCI Express 4 links. And then we have the FPGA section, which is responsible, of course, to collecting data from the 2 provided FMC high pin count slots. And is directly connected on the FAT pipe, so the main intercommunication media in the MicroTCA system, using, of course, a PCI Express interconnection, as I said before. This FPGA is also directly connected to the transceiver that talk on the multi-drop LVDS bus on the backplane, and this way they are able to receive the triggers for the acquisition. On top of that, the card is also capable of providing infrastructure to an RTM that complies to this recommendation for digital D1.4 cards. The second card was developed in the same in-kind, from the same in-kind project, is a digitizer card that also offers an FMC slot available. So the architecture of the card is basically the same as the previous ones, the card called IFC1410. But this time, one of the FMC slots has been replaced and used for a daughter card that embeds analog to digital and digital to analog conversion sections. The Zone 3 connector has been redesigned in order not to provide infrastructure for a digital interface, but for an analog one, so that the input signal will come from the RTM. This way, one can design an RTM with signal conditioning and comply to the input voltage levels of the ADCs. This interconnection will be compliant with the DAISY A1.1 CO standard, which is freely available on the internet. The card also has a clock distribution scheme that allows to retrieve the clock from the backplane as well as from dedicated connectors on the RTM if they are provided. The current mezzanine card that has been developed offers 10-channel 16-bit ADCs running at 250 megasample per second, and 4-channel digital to analog converters, also 16-bit at 2.5 gigasample per second. I will conclude by showing a few systems that are currently under evaluation and development at ICS and ESS, and I will just go on and telling how we're supposed to operate the system. We have a timing card installed into the crate. The main responsibility of this card is, of course, to get synchronization information from an external event generator. This card will be responsible for generating the clock of the facility, which is a 14 Hz clock, and will provide trigger for the acquisition. This is most critical for systems like the LLRF, where we need to be aware of when the beam will actually enter the RF cavities. And, of course, it will also provide information about machine configuration, so which type of beam we're expecting and where we want our beam to stop. The MCH, like always, will take responsibility for monitoring the different cards inside the crate, and it will provide the switching infrastructure for the main communication and the gigabit Ethernet. The CPU will be used for running the EPIC IOC that's responsible for the timing card and for the and for configuring these timing cards. The IFC 1410 in this specific application is used to host an FMC card called ADC 3110, which has 8-channel 250 megasample per second, and the power APC on this card is used to run EPIC IOC. And here on the bottom right side of the slide, we see actually the OPI running on another PC connected to this crate through the Ethernet connection provided by the MCH. A more complete system that is currently under evaluation and development at the Lund University, but also at ESS, is the LLRF system. Here we have, of course, more cards required, but the main idea is the same. We exploit the capabilities of the backplane to provide in the triggering signals that tell the acquisition system where, and of course the control system, where the beam is, so that the PI can act accordingly. And we have timing board providing this information, the ADC card collecting data from the down sample and the down converted input signals, and we have additional cards, RTM cards, developed by Polish in-kind partners that will generate the local oscillator signals and the piezoelectric driving signals for tuning of the cavity. This is a summary of this talk, and since I ran out of time, I will conclude here. So if there is any question.
Maybe time for one question. Fernando?
So how do you plan to interface these crates with the overall control system?
The MCH provides an Ethernet connection on the front panel. So the idea is that we will exploit the interconnection on the backplane, so the gigabit Ethernet links that are there. The MCH offers a gigabit Ethernet switch and then an external interface. So we will use that one to interface to the control systems.
Okay. Do you have any experience with the APMI interface and so?
Yes.
And what is the experience?
So far it's been good. We are planning to develop also an EPIC IOC that will allow us to monitor all the APMI communications on the backplane so that we can also export to the control system what is the status of the different cards, and we can have operators act accordingly.
Thank you.
Welcome.
Okay, let's thank Simone again.